We will be talking about autoscaling a Rails application on AWS. The title is very carefully chosen. All the words are meaningful. So we are not talking about any application, we are talking about a Rails application, the one that we are developing. And not on any cloud, we're talking about Amazon. And right, let's start with who we are in this sentence. So I'm Matti. I'm a developer at GrabCAD. I'm like in a team lead architect role here in Tallinn office. Been doing software for a while now, for about 15 years I think, mostly in the Java world. And now I'm playing with Rails and Amazon. And with me is...
Yeah, I'm Taavi Tuisk. I'm infrastructure engineer in GrabCAD, almost 2 years already. And I have been sysadmin for like 19 years or something. Nowadays, the role is more infrastructure developer, I would say. A lot of coding.
Right. So I'll start first with giving a bit of introduction about who we are, what GrabCAD does, how we run our application, and then I'll hand over to Taavi to talk about how we do the auto-scaling bit of it. Right. So let me start with GrabCAD. What is GrabCAD? GrabCAD is a community of engineers. I think we have the biggest community of mechanical engineers in the world. We have currently 1.6 million users or so. And for mechanical engineers, it's a shared library of 3D models where people can reuse designs that others have done and share their own portfolio with other people. So it's a great resource for both reusing CAD and for students to learn and to publish things that you have done. Besides the library, we also have a commercial product, which is GrabCAD Workbench. You can think of it, I guess, the closest analogy is it's a GitHub for mechanical engineers. So it's a place where mechanical engineers can collaborate on products that they are building. It's an environment where people can share and version files, and where they can see the files without having actually the expensive CAD software. So you can collaborate with non-CAD users. You can comment on models. You can share your files. You can version your files. As you can see from the version number there at the top. And you can see the models right there on the web. And people with non-CAD experience can also have a pretty good visibility into how a project is going. So for example, this is a view of a project that we did in our office, and you can see that you can, for example, do a 3D diff or compare your 3D models with previous versions of the models. And we have mobile apps and desktop clients to work with this. And about GrabCAD as a company, so we have 3 offices here in Thailand, and we have one in UK in Cambridge, and we have in US also in Cambridge, which is a suburb of Boston. We need a Cambridge in Thailand. Right, so that's briefly about GrabCAD. So let's move on to the application. So just to give you a set of, like a context of what we are talking about, I'll give a brief overview of what the architecture of our application looks like. There's a vastly simplified view of our application architecture, at least the bits that are relevant to this talk. So as you may have guessed from the title, GrabCAD is a Ruby on Rails application, mostly. We run a bunch of Rails clusters that serve our application. I drew 2, but there's actually slightly more than that. We run it on Amazon. The application is served behind an load balancer, an elastic load balancer. It's a fairly standard way of running Rails, I would guess. It's a machine with Nginx on the front, and we use Unicorn to run the Rails itself. When serving a request, any machine in the cluster can serve a given request. We don't do session affinity. All the state, that is conversational state between the client and the application, is kept outside the cluster itself. For example, session state is kept in memcache, and most of the rest of it is in our database in Postgres. So the application itself can be considered stateless for meaning of, like in the scaling meaning. Right, so anything that we can push out of the application on the website, we push onto a background job queue, so that's the pipe there. We have a queue for anything that needs to processing, like sending emails or resizing images or any other thing that can be done outside of the request itself. We have a cluster, or even multiple actually, of background workers that takes those tasks and work on them. These workers are also fairly similar to the front-end cluster in the sense that any worker can take a job. The worker has to take care of retrying, of errors, and other like state things. So it's a fairly homogeneous cluster of workers. And in addition to like general odds and ends and cluster background jobs that we have a specialized cluster of model processing where we extract metadata from the 3D models that are uploaded, and we convert those models to be viewable on the web. That's a separate thing. It's a Windows cluster actually, and it's also all of these clusters that are pictured here are auto-scaled. So I can't tell you how many machines there are at this moment because it depends. Right, and in addition we have other things surrounding that as well. For example, search, which is also auto-scaled, and it's also like a cluster in the background. We use Elasticsearch for that. Right, did I miss anything? No, I don't think so. Right, so let's move on. So I'll give a bit of introduction into how we scale this thing. That's, you may notice this is not auto-scaling, it's just scaling. So that's how we did things until up to about the beginning of this year, before we introduced auto-scaling into our application. And right, let's get going. So to do scaling, first you need to get your application running. And that's the step one of it. So you need to have an application that you run that runs preferably already in a cluster, and you need to keep an eye on it to see how it's doing. So you need to have some kind of monitoring on it so that you can tell whether it's doing fine or not. Now, what exactly you monitor for your application, of course, depends. As with everything, it depends on the shape and the structure of the application. So, for example, if you have a background worker cluster, then you probably want to monitor the queue lengths that are leading into the cluster. That's the most reasonable thing. Or if you're running a web application, you probably want to keep an eye on the response times, because if those go high, that's crappy user experience, and that gives an indication that something somewhere is overloaded. Or whatever makes sense for an application. So for example, if you're running a Node.js application, then you probably want to keep an eye on the CPU usage, because if your reactor is taking more than 80% of CPU, then you know that it's not actually reacting, it's computing to something, and that's probably not the place where you want to be. Right, so you keep an eye on your monitoring or on your metrics, and when you see something that goes more like this, then you know that something bad is happening. So you need to take action on this thing, like something is running out of resources somewhere. So that's a place where you know that, okay, changes need to be made. And that's a good graph to show what are the metrics that we actually care about. In this graph, there's this darker greenish colored thing, which is the thing that we use quite often to know whether our application cluster is doing fine or not. So this thing in New Relic is a thing called request queuing time. And to explain what that is, I guess I'll give a bit of introduction into how Rails applications are run and what a Rails application running, like what it looks like. So a Rails application, when it's run on the standard C Ruby distribution, is essentially a single-threaded thing. One process can handle one request at any given time. So for Java people, that probably sounds a bit insane, but that's how things are. For any Rails application, what you want to do is to keep that process, that single process that handles a request, really busy. So you put a queue in front of it, which is Nginx, which accepts requests from the web, and it queues them up and gives them to the Rails process whenever it's ready to process the requests. So instead of a single process, you of course run a bunch of those, and that's called the unicorn, or the unicorn server that takes care of running a bunch of Ruby processes and handing your requests to those. And the request queuing time is the time between when a request hits Nginx and the time between until it's being processed by a Ruby process. So that's the time when it spends just sitting in a queue, not being processed at all. So that's just, from the customer's point of view, that's wasted time. And when you have less unicorn workers available than you have requests coming in, then you get a bit of request queuing. And you know that your cluster is not able to process all the workload that it is receiving. So that's a metric that we keep an eye on very sharply. Right. And in a way, it can, of course, be argued that the reason that we have clusters and that the reason that we need autoscaling is because Taavi is a bit stupid about running things, but yeah, that's how it is. Right, and when you see such a picture, you know that you need to do something about it because things are going bad. So then we get to the next step in the scaling bit, which we call orchestration, which is changing the size of your application cluster, basically. So you can change it up or down. So if you see that you have spare resources, you can remove a machine. If you see that things are going bad, you probably want to add a machine. Killing a machine is fairly simple. You just go and shut it down and remove traces of it from anywhere where it's pointed at. Bring it up is slightly more complicated. I think it involves roughly 3 steps. One is you need to acquire a machine. Depending on your environment, that might take anywhere between seconds and months. In Amazon, it's luckily quite easy. Then you need to set your application up on that machine so that it's ready to process traffic. And you need to add it to the cluster so it's actually accessible by users of that thing. So I want to look at the second step of it, bringing the application up on your machine in a bit more detail, because that's where we found that the complexity is. So on Amazon, there are multiple ways you can do that, of course. The thing that Amazon makes the simplest, I guess, is to have a disk image of your application, the way it will run. Like you will press a golden master, a disk image that you just put up and it's ready to go. Amazon would support that use case really well. It's easy to set up, but unfortunately it has a couple of downsides as well. It's when the machine comes up, you probably want to monitor it, and you want other things that want to use that machine to know where it is. So it needs to advertise its presence in some way, and for that it needs access to some bits of your infrastructure. It needs to know where these are, it needs to have the keys to access those things. And that means that like the image needs to have the keys on it that are basically keys to infrastructure. We found that to be a security hole, so we at GrabCAD chose not to take this approach because we found that it's too hard to secure. It essentially turns the whole image into a secure key, and it's a really big secure key, which is difficult to manage. I think we talked about this about a year ago when we talked at DEVCLUB about CI, I think. Right, and they are slower to generate as well because the images tend to be rather big. So it's something that would slow our deployment process down. And we deploy often. We deploy more than 4 times a day per calendar day on average to production. So we don't want such a thing to slow us down. Right, so let's look at the other approach, what I call growing a server. You get an empty node, or fairly empty node, and then you grow a server out of it by installing all kinds of stuff that you need there and configuring it the way that you want it to be, and installing your application or the latest version of it onto that machine. That has the advantage of having an external entity that takes care of that machine. When it comes up, you will have some bit of code that will go into that machine and configure it the way it needs to be without that machine having to have the keys or the code to the infrastructure. So it's easier to secure, we find, and it gives us a lot more flexibility in a lot of ways. So there are multiple ways to configure that machine. We started with a bunch of bash scripts, as everybody does, I guess, but the bash scripts grew into quite a big thing, like tens of thousands of lines of bash script, which is rather difficult to manage. So we moved on to Chef. We currently configure all of our infrastructure using Chef. That gives us very, very nice properties in a lot of ways. Well, first, it gives us repeatable setup code to build a machine up. But then again, Chef configures machines based on roles, and you can combine those roles. And that has made some things very easy for us. So for example, a year ago, we had a total of 7 test environments, and that was it. So when you wanted to test your code outside of your own dev box, you had to allocate a test environment for yourself. We had a shared spreadsheet, you wrote your name on a machine, you got it, and you knew you had to hand it back after a while because other people also wanted to use that thing. So it was a limited resource. After we automated the whole setup of an environment using Chef, we could have any number of test environments. We can just bring up one by going to a CI environment and asking for one. And in half an hour, you get an email saying that your test environment is there. And the test environment is a thing where you don't need that much capacity. So what Chef allows us to do is to bring up one machine and assign a lot of roles to it. So we actually can pack most of our production infrastructure into one machine. plus one that is Windows machine because Windows, right? But it gives us very nice properties of managing the infrastructure that we have. So you can either bring up a copy of production, which is 14 servers or something. It's a lot of machines that is expensive to run, or you bring up a cheap node and pack everything into that one. So we really like that thing. Right, that is the key to actually getting to scaling, I guess. You need to have a repeatable way to build up your infrastructure really fast and reliably, because that allows you to orchestrate, to change the size of your cluster. So let's take a step back and recap what I talked about. So when you scale your cluster, when you orchestrate it, so then you go through a feedback loop essentially. You run your application, have the functionality up there, you keep an eye on it. You want to know how it's doing. Is it fine? Is it doing too good? Is it being on the load? Then based on the monitoring bit, from time to time you do a decision to change something, scale it up, scale it down, and then you act out the decision. You either kill a node, you bring up a node, install it, add it to the cluster, and then you run it again, and keep an eye on it. It's a nice little feedback loop, as they all are. But, well, keeping an eye on that thing gets kind of boring kind of fast, and people are not very good at reacting fast to changes that occur, and the changes tend to occur when you're not looking. So that's why we wanted to automate away that thing and not have a human involved in that cycle. And that's where I want to hand over the mic to my colleague here.
So, here is the overall flow, how it is built up in the Amazon. And this is just for a brief overview, and we start again with the metrics. Basically, as we told before, you need to monitor your application, but this time metrics have to be available in the Amazon. Because Amazon uses its CloudWatch service as a source of autoscaling, basically data, how to call it. And basically what you can use in the autoscaling are metrics that Amazon itself generates. For example, it's load balancer, you get the latency values from there, or you can send those metrics yourself via the web services API. There's a nice array of libraries available for all sorts of languages like Ruby, Python, or Java, or whatever you need. And the unfortunate thing is that one site, the minimum granularity is 1 minute. So to make decisions, you have to wait at least 1 minute or a bit more if you want to be sure. And also keep in mind that the metrics you use have to be good. Garbage in, garbage out applies here very well. And now we have the metrics in the CloudWatch. You want to define alarms. And alarm is basically a really simple thing. You can be either over the threshold or under the threshold. There are no sophisticated comparators in the Amazon CloudWatch. And alarms are used to trigger actions. So from that we get to the autoscaling group. Amazon alarm actions trigger policies, and when the alarm action is the decision to do something, then the policy is the description what to do. A policy describes what to do, basically adding capacity or subtracting capacity. And how to describe the autoscaling group? Autoscaling group is a collection, or basically is your application cluster, which has a collection of parameters like the maximum amount of machines, the minimum amount of machines, and the then the desired capacity, what you need to run your application with. And the desired capacity can actually be set manually if you don't do any metrics-based scaling. Or you can use this before mentioned metrics and alarms chain. So now you have the chain that moves the cluster up or down, but you need to know what to launch. And this is described by the launch configuration. This describes the system you need to have, like system image, instance type, how the disks are configured, in what security group, and so on. And also one important bit is that the launch configuration has to be recreated when you need to change like the system image and reattach to the, or replace the launch configuration on the autoscaling group. And another nice thing about the scaling groups is that you can attach a load balancer. This is the Amazon's Elastic Load Balancer, and then a lot of things are done for you. Basically, when a node appears, it is already attached to the load balancer. And another important bit of information is that policies have a countdown timer called cooldown. So when a scaling action happens, you get some new instances, then a timer starts, preventing any changes in the autoscaling group capacity. You have to wait for the cooldown to run out, and then next action can happen. Either upscaling when the alarm is still valid, or downscaling when the opposite condition is true. You don't need more capacity anymore. And then, as we talked before, we referred basically, how to say, if you create your systems or you create your servers using the system image where everything is baked in, then this is actually not needed. But we prefer to know a bit more about the hardware we use. We need to test it a little bit. We also need to keep the keys and stuff off the systems and so on. So we have a nice way to know that the node has been created or it has been removed from the autoscaling cluster. And this, the colors here are also important. Basically, the orange services are provided by the Amazon, the notification services, and the scaling worker, the actor that does the actual provisioning. We use Chef for provisioning, but whatever you need to do, this you need to write yourself. But I think it should not be too hard. You get a lot of information from Amazon. So this is a shortened scaling event from the SQS queue, the notification queue. And what you have here is the, for example, the instance ID. This is the important bit of information by which you can find out where your information. You can you can find out the instance and start doing something with it. You can find out its IP. You can basically connect to it, see it when it's running, and start provisioning. And we also like to keep a lot of the information actually in the Amazon attached to the scaling group as tags. So basically you can set your own, how to call, resources there. And we describe the Chef role and DNS record configuration, DNS health check configuration, all that in the tags attached to the scaling group. So all this information comes together into one single point where you can make decisions on bootstrapping or removing the nodes. And we talked about the load balancer before, and that the fact that the instance is attached to the autoscaling group, or autoscaling group attaches the instance to the load balancer automatically. If you don't have health checks configured, then the problem might be that it starts receiving traffic immediately, and this is something you don't want. So you have to configure health checks. And by that, load balancer will know that your application is ready and should receive traffic. And another important bit is in the downscaling, you don't know what instance is taken away, and there's no control over what nodes are going to go. So fortunately, there's a way to tell the load balancer that it should keep existing connections open. This is the, what was it, connection training. So you have like maybe, what was it, 300 seconds or something like that, even more, I think. So this can be used to make sure your customers don't get hurt by downscaling, for example. So the node is not decommissioned before the connection training has been finished. And the big picture again, so to go through this. So first you need your metrics that describe the your behavior of your cluster, and then you can use, for example, queue lengths or whatever you need to. Then there are alarms that trigger on conditions you have set before. And those alarms trigger policies, that those are the descriptions that tell autoscaling group how much should be added or taken away. And then there's the notification chain that tells you that the instances are there and you should do something with those, or the instances are taken away and you need to remove them from monitoring, or if you have I don't know, some records in the Chef server, for example, all of this can be done at that point. You can remove those instances and your system will be in a clean state. So basically, you don't want to leave crap behind. What we have a lot of instances coming and going, and you find out that suddenly you have a lot of records maybe in the monitoring system or something like that that are stale and don't mean anything. So and this is the actual scaling in action. So here you see the queue length rising to some value, and then with a lag, there is the cluster size picking up too. And when the queue has been normalized again, then the cluster starts to go down. But this is a bit of a problem, actually. I will talk about this later. So, and we also have built some tooling around this. There's a lot of resources you need to set to get all this working, and you don't want to fiddle with it with a mouse or on the command line. Maybe 1 or 2 groups, but when you have 16 or something like that, or if you want to reconstruct a copy of production, for example, this becomes a little bit too much. So fortunately, all those resources are creatable via the API. So you can basically use Jenkins to either create all those resources, or in this case we can change those. And learnings. So one thing is that humans tend to leave extra capacity to avoid interruptions. And this can be costly. When the scale becomes bigger, then you pay more for that. And also it gives a lot better availability, we have found. In the night when you want to sleep, you don't want to be fiddling with a cluster or something like that. And when automatics does it for you, you can sleep soundly. You will even not notice that something was going on. And this is a normal state of a system. Another thing that we also found is that the autoscaling cluster is also good when you don't do scaling of capacity. You have a fixed autoscaling group, for example, for Elasticsearch, which is very content with having a node removed or added, and it can rebalance itself, it can recover itself, but this cluster contains data, so we don't want to actually have a monkey with a wrench going on there. And sometimes there are outages in the Amazon. There's a node that can die or something like that. So this autoscaling group works in a way that Amazon notices that the instance is not healthy. It removes it, and it adds a new fresh node to the cluster, to the autoscaling group. And then it gets re-bootstrapped automatically. It gets added to the cluster automatically. And again, I don't have to do anything. It works automatically. And so future. This is the point where we started thinking about metrics. Wouldn't it be good to have the capacity ready already when the traffic comes in? And in the case of the background workers, for example, we actually know that the customer starts doing something like uploading files or something like that, and this is already some kind of metric you can use. So you don't have to use the metric that is connected to some system like the queuing system. You can use something else, like the amount of files uploaded, and you can pre-warm the cluster based on that. So your cluster is ready for the customers' rendering jobs or whatever is done there, and the customers get their results back much quicker.
In case you didn't notice, and on the actual image a couple of slides back, the size of the cluster lagged behind the actual metric that we're watching. What we want to have is that shifted a bit.
We are not there yet, but this is the plan basically. And I guess this is pretty much it. Yeah.